In this chapter, we will talk about work and energy. We will understand all the governing equations that are constraining the work and how to describe work in terms of mathematical description. And after that, we'll talk about the types of energy and how does work affect energy, what's the relation between the force, the distance, the dimensions, the work, and all other types of energy. How does the change in the work value will affect the value of energy? We know in real life that in order to do a certain work, you need to spend a certain amount of energy. When you're biking, you're spending your energy from your muscles to be able to spend that energy to deliver a certain amount of work. Now, if we want to define the work in physical terms, when you are standing in front of the box, you want to push the box to a certain distance. In order to do that, you need a certain amount of force, and you'll be consuming certain amount of energy out of your body. So when the force F acts on an object, resulting in a displacement delta D, distance between the initial position and the final position, a transfer of energy occurs. In this case, the energy transfer is defined as the work being done by that force. If you want to define the equation of work, work equals the force multiplied by the change in distance, or force by displacement. In this case, we have parallel force and we have perpendicular force, and you have a total force with an angle. The work on the horizontal axis equals the force horizontal multiplied by delta D, can be represented as work equals the force by cosine the theta, which is the x component, multiplied by delta D. Let's say we have a force of 150 newtons taking an angle of 0. It's exactly on the horizontal axis, or the x-axis, to the positive side, acting on an object that moves over a displacement of 25 meters at an angle of 25 degrees. What is the work done by this force? We know the force equal, as a given, 1.5 by 10 to the power of 2 newtons. The change in displacement equals 25 meters at an angle of 25 degrees. What we need W. We know W equals F by delta D. In this case, we have F cosine theta to be the parallel force, and we have the F sine theta to be the perpendicular force. So the parallel force here is parallel to the displacement of the object. You can imagine here a box on an inclined surface, same as the inclined surface problems that we solved before. We have F parallel and we have F perpendicular. In this case, we care about the F parallel, which is F cosine theta delta D, 1.5 by 10 to the power of 2 by cosine 25 by 25 meters. That would give you 3.4 by 10 to the power of 3. What is the unit of work? It's in joules. Now, talking about energy, and first type of energy we'll talk about is the potential energy. The object is considered having potential energy if it has the ability to do the work by way of its position or state. For potential energy, there is many forms and types of potential energy. If you want to give an example, we have a ride at the fair where the passengers are lifted vertically before being allowed to drop in free fall. As you can see, they are being lifted vertically, then they will drop in free falling. Ignore the friction in this case. The work done by the machine to lift the passengers and car to a height h equals to a height h equal to the change in gravitational potential energy delta E potential. To lift the object straight up at constant speed, the force applied should equal but opposite to the force of gravity on that object. If you want to represent that in equation to calculate the work, you can develop the equation of change in gravitational potential energy. Delta E potential equals the work, which equals F by delta D. F here is gravitational force because the object is going in free falling. That means, as you know, Fg equals mg. Replace that with mg, then you stumble upon the potential energy equation delta EP equals mg delta h. So the mass by gravitational acceleration by the change in height. So this game has a mass of 500 kilograms. What is the change in gravitational potential energy when they are lifted through a height of 48 meters? Mass is 500 kilograms. We know G, and we know delta H in this case is 48 meters. It goes from zero height up to 48 meters. Find the delta EP, change in gravitational potential energy. Now we can have a convention: up is positive, down is negative. Delta EP equals mg delta H. We have all those variables as givens. So mass would be 5 by 10 to the power of 2 by 9.81 by 48 meters. That would give you 2.35 by 10 to the power of 5 joules. And that is the potential energy exerted on this cart as being lifted up to 48 meters.